When researchers first pieced together the structure of the DNA double helix, their immediate reaction wasn't about raw data. They reacted to visual perfection. Looking at the physical model they had built, Francis Crick remarked that because the structure was so mathematically elegant, it simply had to be correct. The sheer symmetry of the molecule convinced them they had found the truth. We tend to think of science as a cold, emotionless pursuit. We picture researchers poring over spreadsheets, letting the hard numbers dictate every conclusion. But at the highest levels of theoretical physics and mathematics, the process relies heavily on a subjective, aesthetic feeling. These researchers actively look for beauty, a sense of undeniable elegance, harmony, and proportion hidden inside abstract equations. The theoretical physicist Paul Dirac made this his guiding philosophy. He argued that it is actually more important to have beauty in your equations than to have them perfectly match initial experimental data, because data can be flawed or incomplete, but mathematical beauty points toward a deeper reality. This presents a strange mystery. The universe is a vast, unfeeling expanse of matter and energy. Why would a physical cosmos care about what a human mind finds elegant? And how can human aesthetics possibly function as a reliable compass for absolute truth? The clearest evidence linking human aesthetics to physical reality starts with the golden ratio, a mathematical proportion roughly equal to 1.618. Artists and architects have used it for centuries because it looks inherently pleasing. But in nature, this ratio is the absolute baseline for structural perfection. Look closely at this macro photograph of a sunflower. Botany calls this phyllotaxis, dictating how plants pack seeds. Using a divergence angle derived from the golden ratio, this specific geometric pattern repeats across wildly different plant species, defaulting to pure efficiency. We see the exact same geometric rules in this photograph of a pine cone. The spiral scale arrangement follows that same strict mathematical proportion, ensuring the structure grows tightly and protects its core. This diagram shows a standard medical EKG waveform. If you measure the timing between the systolic and diastolic rhythms, the active pumping and the resting phase of a mammalian heart, the optimal, healthiest frequency correlates exactly to that 1.618 proportion. What we perceive as beautiful in biology is not an arbitrary preference. It is our brain instantly recognizing the optimal physical efficiency and energy conservation. This rule scales down into the chemical realm. Incredibly strong carbon molecules called C60, buckyballs, rely completely on a five-sided golden pentagonal symmetry. This table highlights a series of equations known as the golden series. The mathematics behind these stable chemical structures hinge on a unique numerical sequence where addition and multiplication fuse perfectly, with no wasted energy. If we dive even deeper into the subatomic realm, we find the exact same architecture. In 2010, researchers conducted a groundbreaking quantum mechanics experiment, exposing cobalt niobate to a magnetic field. The magnetic field caused the atomic spins inside the material to resonate, acting much like a nanoscale guitar string. The resonance revealed a highly complex, hidden mathematical symmetry, known to physicists as E8. As you can see in this animated diagram of that resonating quantum string, the frequencies of the first two notes it produced were not random. They locked into a perfect golden ratio pitch. Because this specific geometric perfection dictates everything from the way a plant grows to how a quantum string vibrates, mathematical beauty acts as an objective law of reality. This brings us to a major philosophical mystery, best captured by the physicist Eugene Wigner in a famous essay published in 1960. Wigner called his concept the unreasonable effectiveness of mathematics in the natural sciences. He pointed out a glaring paradox. Mathematicians routinely invent highly abstract, complex concepts purely because they find the logic intellectually beautiful. They often have absolutely no intention of applying these formulas to the real world. Yet decades or even centuries later, physicists trying to explain bizarre natural phenomena frequently discover that those exact invented aesthetic concepts are the only tools that solve their equations. If mathematics is strictly a human invention, it is completely illogical that an imaginary puzzle created for fun would perfectly map onto the hidden physical mechanisms of the universe. Take complex numbers, which involve taking the square root of a -1. For a long time, these were treated as elegant mathematical toys with no physical application. Today, the physics of quantum mechanics cannot function without them. This animated diagram shows a flat grid morphing into curved space, non-Euclidean geometries. Mathematicians explored these strictly as intellectual exercises. Decades later, Einstein used these exact invented geometries to explain how massive objects bend space and time, creating gravity in general relativity. Einstein trusted the mathematical elegance of his theory before observational data was in. He believed the equations were too beautiful to incorrectly describe the universe. The paradox resolves itself when we accept that mathematical properties are universally stable. The human mind does not invent these roles. We discover a pre-existing rationality built directly into the fabric of space and time. This is why the beauty principle works. The rationality of human aesthetics perfectly matches the architectural rationality of nature. When a scientist looks at an equation or a structure and senses beauty, they are not imposing their own bias. They are looking directly at the signature of truth.